Salut à tous, alors je suis en Grèce, il est lundi soir 22h, 23h pile poil en fait. Vous savez tous les problèmes que j'ai eu pour m'inscrire tout ça, mais là je suis en train maintenant après le repas de répéter ma conférence qui se tiendra non pas demain mardi mais après-demain mercredi dans l'après-midi. Je sais plus exactement l'heure mais bon je vais checker ça demain, tranquillou. Voilà, donc là l'objectif pour moi ça va être de répéter pour essayer de faire liaison de slide à slide et voir la cohérence de mon talk. C'est un talk que j'avais déjà donné il y a un peu plus d'un an. Je l'ai répété une fois comme ça juste en le lisant. Je l'ai plus vraiment en tête et il y a des choses que je vais devoir enlever sans doute. Voilà. Donc là l'idée c'est juste que je me lance pour essayer d'être à peu près fluente sur les idées, parler, voilà. Donc désolé par avance si ça fourche un peu. J'ai oublié de dire, c'est lettre en anglais. Donc juste je vous traduis le titre. Donc là je vais parler de la préparation des futures analyses post-mortem des échantillons qui sont à base de beryllium qu'il y aura dans le jet ou ITER par la technique de spectroscopie Raman multilongueur d'onde. Voilà, donc le slide est un petit peu blanc au départ, normalement il y a les institutions, tout ça, mais là pour vous j'ai enlevé toute la coloration, voilà, pas de chichi. Donc 3, 2, 1, c'est parti. Je regarde juste l'heure, je vais quand même me chronométrer, histoire de... Alors juste j'ai oublié mon chrono, voilà. Ça c'est de la préparation, ça c'est de la préparation. Presque j'aurais dû le faire en live en fait. Bien. Si, où mon chrono? Voilà, horloge, chronomètre, et c'est parti. So, thanks Mr. Chairman, sign woman, thanks Mrs. Chairman for your introduction. So I will speak about preparing the future post-mortem analysis of beryllium-based jet and heater samples by multi-wavelengths Raman spectroscopy, and I will mainly focus on this. So, first of all, as you may all know, ITER and jet are beryllium and tungsten-based tokamaks. Inside this tokamak, you will have impurities such as oxygen, nitrogen, and carbon, and also many plasma wall interactions. Among others, you will have erosion deposition processes, temperature increase up to 1000 degrees C or even more, and also diffusion mechanism of some species, melting of metals at some points, etc. So many plasma wall interactions that concern first safety issue, which for example you have the tritium retention and dust production, but also material modifications, so diminution of the initial properties by creating mixed materials. So the aims of this presentation is to give you an idea of the capabilities of the Raman microscopy and also to convince you that this technique is able to detect hydrogen isotope and mixed materials by the chemical bondings. So the outlines of these talks: first I will briefly present the work of the different collaborators, then give ideas about basics on Raman microscopy, and then give 3 different results: first varying the amount of defects in beryllium, then implanting deuterium and barium to create BD2 crystals, and then detection of barium carbide formation in codeposit layers, and then I will conclude and give some things. So first, Raman microscopy, the basics. Here on the left you have a scheme presenting an energy, a two-level energy system. So you focus a laser on a sample, you have the light matter interaction. Among all the processes, you have inelastic scattering process that reddish the photon energy, meaning you lost energy, and that by making the difference in energy between the incident photon and the scattered photon, you have access to the vibrational energies of the solid you probe, so that you have an identity card, in fact, of your sample. On the right scheme, you have a typical Raman spectrum. The intensity is plotted in function of the Raman shift. The Raman shift is just the difference in energy between the inelastic and focalized laser in energy and converted in wave numbers. So you have different vibrational modes for your system you are probing, and be careful because not all the vibrational modes are active due to quantum selection rules and also due to symmetry. This technique is sensitive, of course, to chemical bond. If you have BED or BH, the masses will not be the same, and then the vibrator frequencies will change. Beryllium crystals can be probed, tungsten oxide, carbon, and many others. So in more details, in fact, here you have the dispersion of energy in a crystal by the phonons, and then what you have the frequency in function of the K for the phonon in the Brillouin zone, so for 0 up to a value which is close to 10 per nanometer roughly, and you have generally different modes, optical and acoustic modes. And what you have is that because of the filters you cannot have access to these frequencies below the threshold. Second, you have the K of the photon, which is in visible light in the range of 0.01 per nanometer. And as Raman scattering needs to conserve momentum, it means that K phonon and K photon has to be equal. And the only point in the Brillouin zone where you can have this equality is very close to the zone center, the Brillouin center, meaning you only probe generally optical modes at the center of the Brillouin zone. So it's also sensitive to environmental effects due to symmetry mainly, so that it's sensitive to structure, presence of defects, local stress. About the structure, an illustration here, you have 100% of carbon and you have graphite and diamond. And the structures are different, as you know. Graphite is flat sheets, whereas diamond is a 3D structure, and you have different spectra with different frequencies corresponding to these two different structures. It is also a local probe compared to centimetric samples, because the surface probed is roughly 1 micron square. And what about the depth? Of course, depth depends on the optical constants of the material probed. Here, for beryllium, you have an attenuation of the electromagnetic field in the material, which is exponential. And for example, if you use a red laser, you go deep in the material up to 40 nanometer, whereas for green it's 30 and 20 for UV. So changing the laser probes different depths close to the surface, and it is well suited for the supersaturated layer in the community. Oh, it is also a fast technique. One spectrum is typically 1 second and can be as high as few hours depending on the Alton's ratio. Just an illustration here, you have silicon and graphite in semi-logarithmic scale plot with an acquisition time, same conditions, and 1 minute. And what you see is that silicon is higher than graphite, and beryllium is supposed to be Raman active with a mode which is active close to 458 per centimeter. And what you see is really in 1 minute you can detect beryllium easily, but it's less intense than this. And for comparison, we can also detect graphene, which is 1 monolayer. Okay, it's 10 times higher than graphene in intensity, for example. But you can acquire an average on more spectra and have better signal-to-noise ratio, and you see other structures. If now calculation of barium deuterides, which is of interest here, are done by DFT modeling, what you observe is that these vibrational modes, normally some of them should fall in this region, spectral region here, below 1000 per centimeter. So we focus first on these So and now we turn to the results with varying the amount of defects in beryllium. So here we have different samples, and if we focus only on the Raman active mode, here it is for sample 1, which is the less effective, and we increase the amount of defects from sample 1 to sample 4 by introducing other species inside, for example nitrogen. And what we observe is a downshift and a broadening of the peak. But it's not only this. This means that we have tensile stress. But we have also observed new peaks in the wings of this band, which can reach roughly 20% of the total height of this peak. And these new bands here are explained. In fact, if we subtract the Raman active mode, this is the residue. And if we compare the fun and density of state obtained by different techniques, such as inelastic neutron scattering, for example, we observe they are the same. So here, when we have defects in the material, we give rise to fun and density of state by removing some symmetry. We have symmetry relaxation rules. It is then something that tells you you have more or less defects. In the second spectral window, we can have a look on that here. We observe there are broad overlapped peaks and some here also. Compare with the second harmonic of the fun and density of state, which is here just reproduced by multiplying by 2 the wave number of the PDOS. What we observe is a good agreement between all these peaks here. So we think we observe the second PDOS. And if we have a look on samples which have less defects, what we observe is additional sharp peaks here. And this peak, if compared to the position of the E2G and combination modes and second harmonic of these peaks, they are not so far. Of course, they have shifted by anharmonic effects, but they are not so far. So it was a first step to characterize these zones, as some of the deuterides fall in this region. This is given by calculations. So now we turn to deuterium implanted in beryllium at this energy. First, we compare here in semi-logarithmic scale the spectrum in UV of a bombarded and a pristine sample. So what you see is the broadening, which is exaggerated here due to the semi-logarithmic scale plot used, and also the presence of the PDOS. If now we change the wavelengths and take a blue one, what we see is an increase of the PDOS compared to the beryllium allowed peak, and shift on the right of this scale. Redshift. So it means that we have an upshift with lambda L, the wavelengths of the laser. But when we still increase the laser wavelengths, we still have a PDOS that increase with it, a broadening which also increase with it. However, the position comes back and blue shift. So there are different information which are hidden in the PDOS relative intensity and the position of the peak. And we think we have starting of understanding something that may need to go a step further, but this is first step. Here, this is trim calculations that gives you the deuterium implantation profile at this energy. And I have reported the slabs in which you probe your sample by changing the wavelengths. And what you see, of course, is that when you use green, you go deeper in the volume than UV. And here, this is the PDOS intensity compared to the allowed beryllium peak. And it increases from 10% to 25% when increasing the wavelengths. And of course, it's in adequation with the profile, because When you use a green laser, you probe deeper and you probe more defects than closer to the surface. That's why it's more intense, more defects. Vacancy profile given by trim gives you a different shape with a maximum which is roughly close to 15 nanometer. And what you observe is close to the surface. You have a high tensile stress, and this stress is released at the maximum of the vacancy profile and then change again. So it follows more or less the vacancy profile. So the message here is not that we understand well using trim what happens in the material, but we identify two different spectroscopic parameters that give you different information about the gradients from 0 to roughly 30 nanometer, which is sensitive for evaluating in the future the supersaturated layers, which are mentioned many times in the field. Another example now, it is if we vary the amount of deuterium on the surface. Here, position and full width at half maximum, we observe an increase and then we reach a plateau. And this saturation of stress here is reached when we cannot put more hydrogen in the beryllium. We have some tensile stress and then no more evolution. But what we observe by doing some image analysis is that when we reach the saturation, we have appearance of some structure, dots and some dendrites on the sample, which are typically 100 nanometer height. Here, this is an AFM view here. So the question remains now, is there deuterium inside dendrites? And the answer is yes, as you will see. So we use now the Raman spectroscopy in a mapping mode. So a mapping mode means that we put the sample under the beam and we move the sample micron by micron by recording spectra each micron, for example. And what you see here in red, this is on dendrite, and off dendrite, this is the other. And we sum all and compare and normalize, etc. But what we see is that we have additional peaks on dendrite compared as off dendrites. And what are these peaks due? Now we compare with the DFT calculations and we see they fall in the same spectral window with some differences. We can do more by comparing with very recent papers from last year from Pepa et al. In the FIS-RESB. So they use diamond anvil cell and apply the force on a BED mixture to create barium deuterites, barium hydrides, sorry, and they did at the same time XRD and Raman spectroscopy. So what they obtain is all the optical modes which are Raman active and a shift due to the pressure and fast transitions, etc. I don't go into details here. Is just the fact that we have deuterium instead of hydrogen, so we have to reduce the mass. So after applying this known correction, we obtain this and compare to our data. And what we see is that our spectrum looks like their spectrum at 0 gigapascal, no overpressure. And then we can conclude that we have more or less the same spectrum. But the difference is that some points are downshifted, or here there is no sharp peak but a continuum. So it means we have some differences in the structure and we have no more information, right? This one. And now another result, which is about the detection of barium carbide layer. First, DFT modeling. And yeah, okay, and what you see here are in black the frequencies, and on the upper figure plot and on the lower one we vary the amount of barium over carbon in the deposit. On the upper one, what we observe is the barium peak, carbon peak, D and G bonds, which are more or less ordered, and in between broad peaks that looks like the calculations. We have more information here than what I have time to speak about, because we have different wavelengths and things that change with the wavelengths. So we may also have some gradient information, but I don't give you this information here. And on the bottom, what we observe is only the coexistence of two phases, beryllium carbide and carbon. We have no more beryllium, crystalline beryllium islands. But just note that we see a silicon peak, which is the underlying sample holder. So, speak about, in conclusion, we are sensitive to structure, defects, stress in material. This is nanometric depth probe, tens of nanometers, yeah, not a surface. This is not a surface technique, but a near surface technique. It can detect charge and smite bonds and detect mixed materials formation like BEC. So this is a good tool to compare with other techniques. And the next is to understand the BET2 formation by changing other parameters, and also to analyze in the framework of Eurofusion barium oxide and barium hydroxide, for example. And just to your knowledge, from June to the beginning of August, a PhD student from JET came here with her sample, and we analyzed them, and on some of them I don't give you details, but we observed barium hydroxides. So now we are going to understand why. And this is the end of my talk. Ah, ben voilà, j'espère que ça vous a plu. J'ai mis 21 minutes 30 en blablatant un peu trop et en donnant un peu trop de détails à quelques endroits. Donc là, je me suis aperçu des endroits où c'était un peu long. Je revisionnerai la vidéo pour voir où j'ai dit des conneries, parce que j'ai dû en dire. Voilà, il y a des endroits, des petites slides que vous avez vu que j'ai laissé, mais que je vais enlever ou modifier pour donner moins d'informations. Voilà, l'idée pour moi là, c'est de donner un petit peu un goût de à quoi ça sert la technique et comment c'est sensible, pour qu'éventuellement ça déclenche des idées de collaboration, c'est ça qu'on cherche, ou de mise en avant des travaux effectués. Là notamment il y a un papier de 2017 que j'ai pas mis d'ailleurs encore, qui à l'époque où je l'ai fait il n'était pas publié, mais là maintenant il est accepté dans une revue qui s'appelle Nuclear Fusion, et qui est une revue avec un impact facteur de 4. Ça c'est le top, hein. Moi j'ai jamais fait au-delà, hein. Ou alors c'était pas de ma faute quoi, donc voilà, ça c'est un résultat pas mal. Et je parlerai des impacts facteurs, etc. une autre fois, c'est de la merde pour codifier si on travaille bien ou pas, mais c'est très subjectif, mais on en reparlera une autre fois. Là c'est simplement pour dire que je suis crevé, je vais pas tarder à aller dormir. Bah non, parce qu'il faut que que je finisse de lire le papier de revue et que je l'upload là. La deadline elle s'arrête ce soir normalement. Voilà. Non mais du coup j'ai juste à faire quelques petites modifs et c'est dans la boîte. Je répéterai demain une fois. On a prévu de sortir un peu plus demain, d'aller boire un coup parce qu'il y a 2 de mes collègues qui auront fait leur oral. Donc après le resto on va sûrement faire un petit bar et puis voilà, on va voir si on se couche à pas d'heure ou pas. Parce que bah faut en profiter un petit peu, hein. Tant qu'on est là on fait un peu la fête, hein. Voilà, c'est pas tout le temps. Bon allez, à plus et surtout n'oubliez pas de rester critique.